which is called Schmidt Decomposition. I think it's the same Schmidt of Gram-Schmidt. So what is this? You can find some orthonormal bases. That's I for Alice, and this ket I for Bob. And you see that they are aligned. The I's are coordinated, right? They're put together in the superposition. And you can find real numbers that are strictly positive and normalized. And then you take their square roots. There's this thing called probability amplitude. So these are the probabilities. You take the square root, you get what's called probability amplitudes. Okay? And you can write the two-party quantum state like this. Okay? It's actually kind of similar. If you had a single-party state, you could always represent it like this with respect to some orthonormal basis. Well, you would have some complex phases also, potentially. So that's what makes this kind of special, is that these can be chosen real. And you put the complex numbers in these, you encode them in the bases. Actually, you could do that as well if you had just a single party state. So this is extremely useful, and the way that you prove it is, if you're interested in that, we could take any orthonormal basis for the Alice system, any orthonormal basis for the Bob system. I'm calling it J. I suppose we could put phi and maybe psi J in this way. So it sort of indicate that it's not just the standard basis. You can take any orthonormal basis, and then you could write an arbitrary psi in terms of this basis for some complex numbers, alpha ij, that you would find when you take the overlap of this psi with these. Okay? An important point to make is that if you have an orthonormal basis for Alice's system, an orthonormal basis for Bob's system, you tensor them together, that's an orthonormal basis for the joint system. Okay? So when you do this, you get a matrix of these probability amplitudes, and that's what you apply the singular value decomposition to. Okay? You apply it to this matrix of these complex numbers, and then along the diagonal, you'll get the probabilities, and then the unitary on the left and the right of the singular value decomposition end up going into these orthonormal bases. Okay? So that's the rough connection with the singular value decomposition. But it's a very useful theorem for many reasons. It tells us a lot of things. The vector of the probability amplitudes is called the vector of Schmidt coefficients. This D, it's what's called the Schmidt rank of the state. It actually corresponds to the rank of this matrix. You can compute the rank of the matrix, and then the number of singular values is the rank of the matrix. So those singular values will correspond to these probabilities. The probabilities come about because these alpha ij's are not arbitrary numbers. They're constrained to obey the Born rule. The sum of the squares is 1. And so then that gives you that these PI's have to sum to 1. Okay? The Schmidt rank, it's not larger than the dimension of A, the dimension of B. That's the same for the singular value decomposition, right? If I have a dA by dB matrix, like this one, the rank is not going to be larger than dA or dB. The dimensions of the individual, of the number of rows and the number of columns. Okay, so that's a constraint that applies to this D. But it could be smaller, right? For the maximally entangled state, what's the Schmidt rank? It's 2, right? Because you have these 2 coefficients, right? We wrote it. Yeah, we wrote it here. And you have those 2 Schmidt coefficients, right? So previously, we wrote alpha, beta, gamma, delta, right? We wrote this right here, and you see 4 numbers. But what the Schmidt decomposition theorem tells you is that there's somehow better representation, a more minimal representation in terms of this Schmidt representation. So for any pure state, this unit vector of a 2-qubit system, the Schmidt rank, the number, you can always find another basis such that you'd only have 2 probability amplitudes. Okay, so it's somehow a better representation.
Does that go up with if you added other qubits to the system?
So that's an interesting point. What if we made 3 qubits? Is there a Schmidt decomposition? It's not known. But what you could do is you could say, I'm going to make a 2-party cut. So you introduce Charlie, right? There's Alice, Bob, and Charlie. Often the third party is called Charlie. So you could say, okay, I'll make a 2-party cut between Alice, and then I'll group Bob and Charlie together. And then you could apply the Schmidt decomposition theorem to that. And then you would see on that cut, there would only be, there would be no more, it was the minimum of the local dimensions. So that's very interesting, right? It would only be 2, even though you introduced the third one. It has to do with how you made the cut, right? This theorem applies if you introduce an arbitrary number of parties. When you make a 2-party cut, you can apply this theorem. It's not just for, if we tensor together 2 Hilbert spaces, that makes another Hilbert space. So like Alice's system could be 1 qubit, Bob's could be 1 billion. You can still apply this theorem. Okay?
So then, theoretically, you could have n particles.
Yeah.
All of them in this basic optimally entangled state of 2 bipartite.
Yeah, you can always make this bipartite cut, and then if the cut is with respect to 1 qubit and the billion others, then there would always be
but is it always
this right here. The D would be 2.
Is it always 1 to many, or can it be many to many?
It could be many to many. Yeah, you can make the bipartite cut any way you want. And then the Schmidt rank could change. All right, so if you had a 4-party system and you divided it into 1 and 3, the Schmidt rank would be 2. Right? They're all qubits. But if you divided it as Alice, the first 2 were together and the last 2 are together, the Schmidt rank limit would be 4. It could change depending on how you made the cut. Okay, based on how they're grouped together. So that's very interesting. For pure states, there's a simple way to decide the entanglement problem, right? We talked about that previously for density matrices. Given a description of a density matrix, how do you decide if it's entangled? For density matrices, that's what we said was hard. We said it was really hard. But for pure states, it's easy. You do the Schmidt decomposition, okay? The Schmidt decomposition is, we said it's essentially the singular value decomposition. That's a linear algebra operation. So that's polynomial, that's, order d to the 3, where d is the dimension of the matrix. Okay, so that's something you could do fast. Now, maybe you have to define what you mean by fast. The dimension is exponential in the number of qubits, right? Like if I have n qubits, the Hilbert space dimension is 2 to the n. Okay. Actually, we didn't really talk about that yet. But you can see it, right? So we said 2 qubits, you tensor together, you get a 4 by 4, right? So that's 2 to the 2. If you have 3 qubits, you would tensor together 3 of these 2 by 2s, that's an 8 by 8, right? The dimensions are multiplying. So then 8 by 8 is 2 to the 3, etc., right? 4 qubits would be 2 to the 4, 16. So the dimension is growing exponentially with the number of qubits. And that's another reason why you can realize these complex calculations in quantum mechanics. Because you have this exponentially large Hilbert space for just a linear number of qubits. Okay.
That last line is a little strange because for qubits isn't D always at least 2?
Yeah, you need 2 you need the Schmidt rank to be 2 for qubits.
So what is the content of that last statement? Is it entangled?
Oh, if you consider, if we go beyond qubits, right? So if Alice's system is dimension dA, right? Bob's is dimension dB.
But I'm saying, isn't it always, is it D always going to be at least 2?
Sorry, I guess I'm conflating the D's. So I use D to mean Schmidt rank in this context, right? So Alice's dimension could be dA, Bob's could be dB. You do the Schmidt decomposition calculation, you'll get a Schmidt rank. That's the number of strictly positive probabilities. And then we say it's entangled if that Schmidt rank is larger than 2. Then it cannot be written as a product state.
Seems to be very limited that only says when D is equal to 1.
Yeah, that is a product
May
state,
not be
right?
entangled.
When D is 1, you just have one term in the sum.
Mhm.
That's it. And then it's a tensor
Sort of
product.
trivial.
You could consider it trivial, yeah. But it's an easy way to decide, right? So for pure states, the entanglement problem is easy. You just do the singular value decomposition. It becomes hard when you consider mixed states and the definition of separability that we talked about, right? Okay, another tool, partial trace. I guess we want to get to interesting things like teleportation, right? So we have to maybe go faster. The trace of a matrix you can write like this. That's an important calculation. That's how we defined quantum states, that they're trace 1. So how can you calculate trace? You take an arbitrary orthonormal basis and you do the sandwiching and sum. And then you get the trace. And then it doesn't matter what orthonormal basis you take. Partial trace is exactly that. You take an arbitrary orthonormal basis for Alice's system, you tensor each of those vectors with the identity for Bob, okay? And then what does this mean? For example, for qubits, mathematically, I think it's important to write out. So I could pick, 0 and 1. And then when we do this, we literally mean, and suppose we're just dealing with qubits. This means censor this with the identity, okay? And then right on the left, as we said before. So 1, 0, this, and then 0, 0. So you do that construction, and that's what this means. Okay? But physically, you should think that it's like, we were talking about local density operator, global density operator, right? This is what we use to figure out the local density operator. So the trace is like discarding. That's how you think of it. And it's akin to marginalizing a probability distribution. So this is like you're doing nothing on Bob, and you're discarding Alice's system. So when you sandwich the y with these vectors in this way, it'll contract. If we're dealing with qubits, the YAB is a 4 by 4. This operation will contract a 4 by 4 to a 2 by 2 if you work out the calculation. Okay, I guess you can see it here, right? So if we had a 4 by 4, etc. And then I'm out of room. I'm not going to write here. We would multiply. We would multiply with this, and that contracts to a 2 by 2. And then you do the same thing with 1, and you sum, and then that's the partial trace. Okay. So that's a really important operation because if we have a global density operator, we might be interested in what, how you describe only Alice's state, right? The state of Alice's system if Bob is simply not available. And it's a linear operation, which is of course very nice. Okay, so we already started talking about the interpretation of partial trace. Suppose that Alice and Bob's quantum systems, say qubits, are described by this density operator, rho AB. Then if we're interested in figuring out the state of Alice's system alone, we use the partial, sorry, the state of, there's a typo. I apologize. This is, it should either be rho B or it should be trace B. Okay. Yeah, can't win them all. So anyway, if we do the trace B, the resulting matrix describes the state of Alice's system alone. If Bob's system were somehow not accessible, if it were lost in the environment or whatever. Okay? And then we can use this rho A to predict the outcomes of experiments that are conducted on Alice's system alone. Right? So this is what we were talking about. If we didn't pull together our data when we did this tomography experiment, then we could only calculate or estimate the local density matrices.
Okay, so there'll be akin to Bob's information not just being accessible because we have
Right.
not communicated that information.
That's right.
It's literally inaccessible.
Yeah.
Okay.
But then if we pull together the statistics, we can figure out the global density matrix. This is what we said earlier. Partial trace generalizes this notion of marginalizing a probability distribution. Right? Earlier we said anything we can do classical, we can do quantum. So we can take a classical joint probability distribution and embed in a quantum state. How do we do that? We pick an orthonormal basis for the X system, an orthonormal basis for the Y system. And then this is just placing the probabilities along the diagonal. Okay? Then if you do the partial trace, one thing you can prove, we stated that partial trace is a linear operation. So then what does that translate to? The operation we showed previously is equivalent to doing an individual exchanging the trace with the sum in these scalars and doing the trace on these. Okay? Then you can prove. We didn't show it. You can prove it. And then when you do that, these have unit trace, right? A unit vector, I don't know if we said that, but you know, if you have a unit vector and you do this trace, then this is the same as the overlap. Okay? And for a unit vector, the overlap is 1. Okay, so you do that, and then that ends up being the same as summing over the y's, all right? And so that's this operation of marginalizing a probability distribution. That's what you do classically if you're trying to figure out the distribution that describes Alice's system alone. If Bob is inaccessible, you do this marginalization. Okay, and you end up with a marginal probability distribution, and the quantum generalizes the classical. This would be the state corresponding to a classical marginal probability distribution, which is defined like this. Okay. There's a very important concept in quantum information. This is one of the big things that distinguishes quantum from classical. It's the notion of purification of quantum states. Okay? So we'll start by purifying quantum states. You can purify not just quantum states, you can purify quantum channels, you can purify quantum measurements, you can purify anything. Okay? And so let's start with states. So the strict definition is this. Suppose you have a density operator on a system S of interest. Okay? And you know, we said that's a positive semi-definite unit trace. A purification is a pure state that can be written as this psi on a tensor product over space. So it's like if S were a qubit, it would be a state of 2 qubits. that would purify the state of a single qubit. Okay? And this is the definition. Psi is said to purify rho, or be a purification of rho, if, when you discard this reference system R by partial trace, you recover the original density matrix. Okay? So, this is different. You cannot do this classically. What is the claim? What would you try to do classically? You would take a distribution, and then you would try to find some deterministic classical state on a joint system, such that when you do this discarding, you recover a mixture, a mixed state. Okay? But what is a deterministic classical state? That's what we said earlier. For a bit, it's either 0 or 1. That's it. There's nothing else, right? On the Bloch sphere, it was the North Pole, the South Pole. We couldn't do anything else with the other elements of the surface of the Bloch sphere. Okay. So the claim classically would be, oh, I could take a mixed probability distribution and find a deterministic state of 2 bits. What is the deterministic state of 2 bits? There's only 4 possibilities: 0, 0, 0, 1, 1, 0, 1, 1. When you trace out, when you marginalize those deterministic states, you get a deterministic state. You get back, if it's 0, 0 and you discard Bob's bit, you get 0. If you have 0, 1, you discard 1, you get 0. So you cannot do this classically. So that's a distinct separation between classical and quantum. Okay? Some people, a research program is to figure out simpler postulates of quantum mechanics based on information. Okay? And one kind of notion that emerged as a distinction between classical and quantum is this purification. Okay? So if you make that a postulate that purification exists in your theory, then that's a way that you can distinguish classical from quantum. If you're starting from this foundational bare bones perspective, where you sort of say, we're not going to use Hilbert space, we're not going to use these things, we're going to start from these information notions and then derive quantum theory from that. So that's a research program that people have explored. We saw how we said Bell was the first quantum information theorist, right? That was pure foundations of quantum mechanics. So a lot of people who were thinking about foundations of quantum mechanics, they kind of migrated to quantum information, okay? But in the field of quantum foundations, there's kind of a lot of wacky people with wacky ideas. So this merger to quantum information, it kind of applied a filter in some sense that to do work in quantum information, you have to be serious. You have to show that these things could be observed experimentally and found. Okay. So, but a lot those communities, the serious people in quantum foundations, a lot of them found like a new home in quantum information. Okay. Anyway, so how do we, if we're given a density operator, how do we construct a purification? It's actually a simple recipe. So if we have a density operator rho, that's what we're saying over here, we have the spectral decomposition theorem, right? So there we get these, there's some orthonormal basis, and then we have these probabilities along the diagonal. And then what you do is this recipe. You take the probabilities, you make them probability amplitudes, you flip this bra to a ket, and you put it to another system. Oh, sorry, you flip this bra to this ket on the reference, okay? And then you tensor them together. That's a purification. That's a standard recipe, okay? And then you can check that when you do the partial trace over the reference, due to the fact that this is an orthonormal basis, it'll collapse, you get Kronecker deltas, and then it'll collapse to this original density matrix. Okay? So as an example, we talked about two kinds of states. We talked about the classical random bit state, which was the identity matrix divided by 2. Right? And then we can write that as 1 over 2, 0, plus 1 over 2, 1. If we follow this recipe, this is a spectral decomposition. The purification would be the probabilities you take the square root, they go to probability amplitudes. The bras go to kets. What do you get? The maximally entangled state, which we talked about. Okay. So the maximally entangled state purifies the maximally mixed state.
Now, however, as a physical operation, is it always possible because flipping kets to brass involves things like time reversing and so on?
Yeah, this is, I would say, a mathematical construction. You can interpret it in a physical way. You can say that this random noise in this single quantum system, you could, if you were to think about that noise in a classical way, you could think of it as lack of knowledge. Right? Like I flipped the coin, and then you didn't observe everything that happened, and then I covered it, and then it's just a random mixture. That's how you would describe it. And that's due to lack of knowledge of all the things that are going on. You just say, oh, okay, it's a random bit. With this picture, it gives a different way of thinking about noise. The noise is somehow due to entanglement with an inaccessible environment. Okay? So there's this other qubit out there that's entangled with the qubit, the bit we're flipping. And the reason it looks mixed is due to this entanglement. That's another interpretation. Okay? And it's a useful interpretation. Okay? So that's the quantum information interpretation of noise, that noise is due to entanglement with an inaccessible environment. Somehow, this system
inaccessible meaning the rest of the universe or something?
Rest of the universe. You could just draw a line, you could draw a box around yourself and say, okay, this is me, rest of the universe, I'm entangled with the rest of the universe.
Makes sense to me.
Makes perfect sense.
Well, at least the rest
great.
of the universe is big, but otherwise there must be some limit on the dimensions
Yeah.
of the RNS.
So that's the Schmidt decomposition coming into play, right? So the Schmidt decomposition would say, for a qubit, it suffices to model the entanglement with the rest of the universe by just a single qubit.
Yeah, but you can't generally.
Or just two distinguishable states, right? So if the rest of the universe were 1 billion qubits, you could say, oh, okay, this could be 1 billion zeros and 1 billion ones for the rest of the universe. And those would be two distinguishable states. You would just end up with two terms in the superposition. Okay. This is an important notion. Two different states. You can have two different purifications of rho s, right? So earlier, I don't know your name, but you mentioned if we set alpha and delta to 0, we would get 0, 1 plus 1, 0, right? So that could be a different purification of the maximum mixed state. I could do this, and it's still a purification, right? So what the next thing you want to figure out is sort of a what's called equivalence class of these purifications. So you have this freedom in purifications, right? You can have multiple different purifications of the same state, but the constraint is that they must be related by a unitary operation acting on the purifying system. That's something you can prove, okay? And here, how would you get from the purification that I wrote to your purification if we apply sigma x, the bit flip operation, on this reference system, are here. The x, it's a bit flip, it would flip 0 to 1 and 1 to 0. So that's the unitary that would relate those purifications. Okay. I think we have to just go a bit faster. I'll be here. Or, you know, I'll eventually be talking to 0 people. So we're saying this concept doesn't exist in classical information theory. We already talked about this interpretation. You can interpret noise as being due to entanglement with an inaccessible environment or reference system. There's a very interesting cryptographic interpretation which is useful for quantum cryptography. Okay? Yes. So in a cryptographic system, maybe the protocol, it runs, it does a bunch of things, and then it eventually generates a state of 2 qubits, let's say. Right? And the state of 2 qubits is described mathematically by this rho AB. If we're completely paranoid, as you should be if you're designing a cryptographic system, then you would want to protect your system from the rest of the universe, right? So you would say that, let's just say that the eavesdropper has access to the full purification of this state. Okay? So it's a 2 qubit state, it's a density matrix, and then that can be purified also. Any density matrix can be purified. Right? And if you do so, then you're guaranteed, if quantum mechanics is correct, as we believe it is, that if you generate a state that is somehow in a tensor product with Eve, the eavesdropper, then you're guaranteed that whatever Alice and Bob observe is independent of what Eve observes. Okay? For example, suppose that by your protocol, you had this wonderful cryptographic protocol where you could make the Bell state, the maximally entangled state, which we wrote down, you know, this is the vector corresponding to the maximally entangled state. Suppose you could make that state. That is a pure state. And so the only way you can purify it is with a tensor product pure state. Okay? That's from the Schmidt decomposition theorem. So let's write that down. Suppose that with the protocol you can make this. Let's call that phi and b. And then we said the density matrix is this one. One's in the corners, zeros elsewhere. That one. Okay? And then we wanted to think, what could be the possible state of any other system in the universe, you know, that this could be entangled with or correlated with, okay? So the claim is the only possibility, you know, the goal, what we're trying to think about is, what are the possible three-party states such that when we trace over Eve, we recover this phi EB, this maximally entangled state. Okay? So the claim is, from the Schmidt decomposition theorem, if you make a bipartite cut between A, B, and E, you can conclude that the only possibility is that rho A, B, E there's some other density operator for Eve, and it must be in tensor product with Alice and Bob's state. So that's something that is very interesting, and anything interesting deserves a name, and it's called monogamy of entanglement. Okay. This whole thing together. is called monogamy. And it means that if Alice and Bob are in a maximally entangled state, then there's any other party cannot be maximally entangled with Alice or with Bob. So there are no polygamous entanglements.
There's no
But they cannot be maximally entangled.
But
It
even
would be 99%.
yeah, but it's true also for pure states.
It
Similar
creates an
reason
Eberhard state,
applies.
right?
What's that?
It creates an Eberhard state.
Creates a what state?
An Eberhard state, where it's 1 over root 1 plus some r or something instead of
What did you call it? Steve?
Eberhard.
Everhard?
E-B-E-R-H-A-R-D-T.
Oh, okay. I don't know that state. There are many states.
And this could be any dimension, right?
This is any dimension. Yeah. Yeah, so if you were to sit down and try to mathematically construct some density matrix of 2 qubits and E arbitrarily large, whatever, and try to find such a state that's consistent with this local state, you would not find anything other than this. Okay? You could sit for years.
I think that was Eberhard's paper came out, I don't know, a couple of years ago, and the point of it was that if you end up with a 1 over 1 plus r, root 1 plus r, then you realize you're not maximally entangled, and so you add an eavesdropper.
Yeah. This is also true if you had a pure state here. Any pure state. This is also true. So it would also be true if the Eberhard is a pure state. It would also be true. Okay. So why is this related to cryptography? So if your protocol can make this maximally entangled state, then Alice and Bob could do local measurements in, say, the Z basis. We haven't talked about measurements yet, sorry. But they could do measurements, and they would end up with the situation where if Alice measures 0, Bob would also measure 0 with probability 1/2. And if Alice measures 1, Bob would also measure 1 with probability 1/2. That's a uniformly random outcome. So it's hard to guess if you increase the number of times this happened, right? If I had n of these and I did it n times, I would get random, uniformly random and perfectly correlated bit strings. That's a secret key, okay? The uniformly random and perfectly correlated bit string is independent of whatever Eve would observe. So that is a perfect secret key that you can decode from the maximum entangled state. So that's why in all these entanglement-based quantum key distribution protocols, the goal is to make this state, okay? And then there's questions about how do you verify that you have entanglement. For that, you can use Bell inequalities. So that's the connection between the foundational work of Bell and modern quantum cryptography, okay? That was discovered by Arthur Eckert in 1991. Okay. We're going to talk about quantum channels. I think we should go fast. We're going to go fast through this part. Classical channels, what are they? They're conditional probability distributions, okay? So they take a probability distribution of the input to a probability distribution of the output. It's just a stochastic matrix that has certain properties, blah, blah, blah. Okay, quantum channels, they should generalize the notion of a classical channel. So you make constraints, okay? They're physically motivated reasons why you make these constraints. We have to go fast. So it should have a linear action on the space of density matrices. There's good reasons for that. A quantum channel is supposed to be a physical quantum evolution. It should take a quantum state to a quantum state. So it should take a positive semi-definite matrix with trace 1 to a positive semi-definite matrix with trace 1. So that's what's called a positive map. It preserves positivity. And it should preserve the trace. So that's called trace preservation. So you want those properties so that it makes sense. There's a notion called complete positivity. I will just describe this with a box, with a diagram. Okay? So I'm going to draw an entangled state like this. Here's a reference system, here's Alice system. This is meant to denote there's particles that they have to interact at some point in time, and then they go over quantum communication channels, and then Robert has one, Alice has the other. And then if Alice applies an evolution, physical evolution, to her system, it could transform the system into something that goes to Bob. Okay? The state of these systems should be it should be a quantum state, what we describe this as mathematically. So this channel should take a quantum state to a quantum state. It seems obvious, but it's beyond the notion of a classical channel, because it has to work for entangled states which can't be described classically. So that's how you have this notion of complete positivity, that if you do nothing on one system and you evolve the other, the result should be a quantum state. So that's complete positivity, and that's the mathematically and physically sensible thing to require for quantum evolutions. Okay, so we summarize that with this. And then, forget that. It is important, but this is very important. You can write any quantum channel in this form. Okay, so the quantum channel is a map. It acts in the space of density operators, and it takes a density operator to a density operator. So if this X is some density operator, then it evolves in this way. And these KIs are arbitrary matrices that are required to satisfy this constraint. That when you sum the squares, you get the identity. Okay? So that's a theorem that you can prove. That was the point of these slides. If you say, I demand for my evolution that it be linear, which is sensible, that it be completely positive, which we argued is also sensible, that it be trace preserving, you arrive at the conclusion that it can only have this form. Okay? So that's a mathematical theorem called Choi-Krauss theorem. Okay? And so any quantum evolution can be written this way. What's an important example? Unitary evolution, right? So suppose the evolution is unitary. Well, to be unitary, U dagger U has to be the identity. So there cannot be the sum for a unitary evolution. There's only one Ki, there's only one K, and then you get unitarity. Technically, it's not unitarity. It's something called an isometry, but it's pretty much a unitary. Okay, so that's how you get unitary evolution as a special case of a quantum evolution. Good. What are examples? This is a nice one. It's a very simple toy model, bit flip channel. So how do you interpret this? You send the qubit through the channel. It either goes through, or, so it goes through with some probability 1 minus p, or a bit flip applies. Okay? So that's the sigma x. So if you were to send in the classical state 0, the output would be, a mixture of 0 and 1. Because the bit flip would flip the 0 to the 1. Okay? If you change x to z, that's what's called dephasing channel. So it's like a bit flip channel at a different basis. Okay, so it's called dephasing channel. That's a common model of noise in superconducting qubits, common toy model. There's something else called depolarizing channel. So it's a bit worse of a situation. So you either, you send the qubit through, it either gets through with some probability, or it just gets completely discarded and replaced with a maximally mixed state. Okay? So it's called depolarizing noise. And if you look at it as a block sphere, you have the block sphere, you have the state of your qubit on the block sphere. This is just a contraction towards the middle, towards the middle of the sphere. Because the middle of the sphere corresponds to the maximally mixed state. And so it's just sort of, if you were to keep applying this over and over again, eventually, after an infinite number of applications, it would just converge to the middle. Okay? to the completely random state. And then your state is said to be completely depolarized and completely useless. Okay? There's another model for a quantum channel called the quantum erasure channel. This is a very rough model of communication over fiber optic cable, right? Like a lost channel. So suppose you encode your quantum information into the polarization of a photon, right? So there's a photon there, and it's a superposition of being horizontally or vertically polarized. That's the qubit that we're thinking of. If you send this through a lost channel, there's a chance that the qubit would be lost, and then what you get at the output is called vacuum state. You know, it's just no photons are there. And so that could be this erasure symbol that is orthogonal to what you sent in. Right? So what you sent in is a single photon, either horizontally or vertically polarized. Those are distinguishable states. And furthermore, they're distinguishable from the vacuum if there's no photon present. So that's this erasure channel, and we study that quite a bit. If you're trying to study some kind of problem in information theory, this is the nicest one to start with. So you start with that. Okay. We talked about unitary channels. If there's just one Krauss operator, then it's a unitary matrix. These are the ideal reversible channels that you want to implement in your quantum computation, right? So if you're doing some quantum algorithm, it's some list of instruction, it's some instruction sequences that says, you know, do this gate, do this gate, do this logic gate, and you're trying to realize unitary channels, okay? So, but in practice, you cannot do so, and you realize noisy channels. So then, if a quantum channel has more than one Krauss operator in that sum that we wrote, it is non-unitary and thus irreversible. Okay. I'm going to skip this. Very important is a measurement channel, right? So quantum measurement is a very special kind of evolution in quantum mechanics. But you can also phrase that in the language of quantum channels, okay? And so a sort of interesting and unifying conceptual approach in quantum mechanics is you just say everything is a quantum channel, you know? So there could be a single postulate, if you want to simplify the theory as much as possible, and the postulate would just be everything is a quantum channel. Okay? So you can write states as channels, you can write measurements as channels, you can write unitary evolution as channels, partial traces as channels, measurements as channels. Okay? That's something I'm not going to prove, but it's something that's true. Measurement channels take quantum systems as their input and output classical systems, right? So that's how we think of a measurement. You know, you do some, you're trying to observe something about your system, right? You have this device that you use to measure the system. For example, you know, if you have a photon and you're trying to learn something about the state, you could do a polarization measurement, right? So if the quantum state were this alpha H, horizontally polarized, plus beta V, vertically polarized, you could send the photon, the beam of light that's described by this state through a polarizing beam splitter. And what does a polarizing beam splitter do? It, for example, lets through the H, or it reflects the V, okay? And then you can put photodetectors here. If the situation is ideal, what will happen is with probability alpha squared, this photodetector will click and this one will not. Right? So the state will undergo this distinct evolution. It's sort of forced to one of two outcomes. Okay? The other possibility is that with probability beta squared, this photodetector will click, the vertical will go through, and this one will not. Okay? So if the situation is ideal, those are the only two outcomes you'll observe. If it's not ideal, maybe there'll be some loss, the light will somehow scatter off this beam splitter, and you could observe no clicks, right? There would just be vacuum. That would be the erasure channel that we talked about earlier. Okay. How do you phrase it as a quantum channel? You do it like this. This is the most general way you can write a quantum measurement. So it's an evolution from the density operator rho to a probabilistic mixture of classical states. Okay? What do? You take the rho, you trace with an operator that's positive semi-definite. This is called a measurement operator. And the measurement operators are constrained to satisfy this it's called completeness relation, because they sum to the identity. Okay? And that's so that what you observe, the sum of the probabilities that you observe should be 1, right? Because that's, the full sample space of possibilities. So those are the constraints, and that's how you write any measurement as a measurement channel. Okay? And then these classical states corresponding to what you observe. The click in one port or not in the other port, or vice versa. Okay. Another interpretation, which is related to what we were saying over here, is that the measurement channel is returning this classical value x with this probability. That's sort of the traditional interpretation. That's another way of writing the Born rule. Okay, so the Born rule we said was that this alpha squared plus beta squared has the sums of 1. This is a generalization of the Born rule. Okay. Yeah.
How does one obtain this mx operator? How's it built?
So that corresponds to your device. You would have to characterize your device in some way. You would have to know. That's a good question. You have to measure the measurement, right? So, how do you measure the measurement? It's a good question. I mean, here we're assuming the photodetectors are ideal. So if we knew, I don't know how to answer your question quickly and in an intuitive way.
But
It's a very good question, because measurement is what we use to interface with the quantum world. We're somehow classical and we interface with the quantum world. But then we have to characterize this measurement in some way.
Okay, but it's something non-trivial. It's not just like you take the projection of x. This would probably not be mx, because it would also be an operator.
It's a very good question. So I mean, I can answer it in a maybe not so good way. Suppose that we could prepare an arbitrary quantum state of a quantum system, and we knew that we could prepare exactly that state that we desired, right? I would say, I want the quantum system to be prepared in the state rho. And then you send that to some box, and then voila, it prepares that state. Okay. So this is how it's not so nice to answer your question. But suppose you could do that. Then you do your measurement, right? Then you observe some probabilities. Then you could, if you could prepare any quantum state, you could start characterizing these operators, right?
Mm-hmm.
So, that's some indirect way of answering your question, but then you could ask, well, how do you exactly know that you're preparing these quantum states, right? So,
That's a good method.
I don't know how to fully answer the question. Yeah.
But I'm satisfied. Thanks.
Okay. So, yeah, we write them as this. There's a very nice video that came out that I would like to show that illustrates this principle of quantum measurement. And it does it in 3 minutes. How do I make this? I want to make this full screen.
So double click
Double click? Where?
in the middle.
Oh, thank you so much. So this is the video. So you can hear the music? Is it low? So the music corresponds well with what's going on. So this just goes on and on. It's like singing na 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 and Hey Jude. You just do it many, many times and enjoy it. That's it. That's really nice. How does the music correspond to what's going on? Anybody catch that?
There are more notes, right?
More notes when what was going on?
When you don't observe the system.
Right. And what does that correspond to?
Well, that you have superposition of different states.
Correct.
The
And
notes
then-
are the weights.
Yeah. And then what would happen when you would look with the music?
Yeah, you get
Sorry,
only
we're
one
not
note.
gonna What's that?
You get only one note.
You get only one
I
note.
mean, one.
So just, everybody knows? All right. Maybe it's obvious.
But I mean,
It's
you
very- it's
kind
very
of,
nice.
you
I
kind of
didn't say
said
anything
it.
like
You,
that.
you said, oh, listen to the music. It makes perfect
Yeah,
sense. Oh,
okay.
otherwise, I wouldn't
Good.
notice.
Right. Okay.
You didn't notice?
That was made by, that was the winner of some competition in Singapore for quantum short movies. Okay, we're about to hit 8:30. That was the promised ending time. I could go beyond that if you want, but why don't we jump to the Bell experiment, okay? And we'll skip some stuff, because I think that's very interesting to play and to see. And I have some coins from Poland that we can play with. I couldn't find quarters, and you know, the other day I went to try to get grandma's cookies downstairs, and these were completely useless. Okay, so how is quantum information different from classical? That we can illustrate with this Bell experiment or the modern phrasing CHSH game. So one way to answer the question is to figure out a task for which only a quantum strategy can outperform a classical one. Okay? And this is the famous Bell experiment. This is an experiment that people had been trying to realize for years in a loophole-free way. Okay? So what does that mean? There are different kinds of loopholes that can come into play when you're actually trying to implement these Bell experiments. Okay? One is called the detection loophole, and this is that sometimes your detector won't fire, right? So like if the channels over which you're doing the experiment are very noisy, or if they're happening over long distances, there could be loss, right? And we talked about that. We said if there's loss, both photodetectors would not fire, right? And then the photon would be lost, and you simply wouldn't be able to observe it. And so then for those runs, you didn't really know what happened, okay? And so there could be something going on other than this entanglement. And so since you simply didn't know what happened, it's a loophole with this Bell experiment. That's the rough explanation. Okay. Another loophole is what's called the locality loophole. The particles for which you're doing the Bell experiment, so the Bell experiment is, you need to have two photons, for example. Maybe you have some what's called EPR source, and then it sends something to Alice, and it sends something to Bob, and then you do these polarization measurements. Okay? These local stations need to be far enough apart such that Alice and Bob would not be able to communicate classically to coordinate their responses to the questions in the game. Okay? So if they're not far enough apart, which is dictated by the speed of light, so you need to do some calculation about how quick your photodetectors can fire in response to this EPR source, and factor in the speed of light. If they're not far enough apart, then you could say, oh, well, in principle, Alice and Bob could have communicated some signal and cheated the game. So these two constraints, detection loophole and locality loophole, to overcome simultaneously, it's difficult, right? Because they have to communicate, this distribution of the particles has to be far enough apart to overcome the locality loophole. But then you're communicating over, you're sending these over far distances, and there could be loss, and then you succumb to this detection loophole, okay? And the detectors need to be good enough to observe what's happening. And so to overcome both, that was very difficult, and it was only done recently, okay? There's another loophole called the memory loophole, and that's, there could be weird things going on from trial to trial. You have to do this experiment over and over again, and so there could be like memory effects between the trials. Okay, so that's another loophole that has to be overcome. And it's kind of a remarkable story. There's a researcher who will present tomorrow. His name's Peter Bierhorst. During his PhD at Tulane, he was working in the math department, essentially on his own. His advisor didn't really, well, I shouldn't say that. I don't know if his advisor knew much about Bell experiments at the time that Peter was doing his research. Okay, and maybe he would admit to that. I don't know. He was a mathematician. Anyway, so Peter did this work, and his work was to overcome this, figure out ways to model statistics such that you could overcome this memory loophole. He came here and presented his work, and then there was a unnamed member of the audience who was making fun of him during his talk, and saying, oh, you're worried about the little gremlins in the experiments throwing off statistics, blah, blah, blah. And then Peter, he was asking, oh, where can I apply to do postdoctoral work? Who would be interested in this? And I said, oh, there's people at NIST Boulder who I think would be very interested. They're trying to do these Bell experiments. And so he applied there, and he got a postdoc. And then his theory in his PhD thesis went into one of the experimental papers for the loophole-free Bell test, you know, that overcame all these loopholes at the same time. And his was about the memory loophole. And so that was really amazing, and you'll get to see him speak tomorrow. So he's at UNO now. Good. What is the Bell experiment? It involves two spatially separated parties, Alice and Bob, and a referee. Okay. Who wants to be Alice? Okay. You were Alice at QCMC, is that right?
I was actually,
Okay.
that's
All right.
fine.
So you were always Alice. And then who wants to be Bob? Anybody? Please, Bob.
Wow.
It requires, it's, okay, you laugh, so you're Bob. Good. All right. So it involves Alice and Bob, and I'm the referee, right? So I stand here like this. And I flip coins. So I'll do that now. One will be heads, and the other thing is tails. Okay. Don't talk to each other. You need to not violate the locality loophole. Okay. So don't talk to each other. All right. And good. So you can look at your local outcomes. And heads will be 0, and tails will be 1. Okay.
I've never seen this coin before, so I don't know which one is which.
Right. So the one is heads, and the other thing is tails.
Okay. One is heads.
Yeah.
You can
So you have to say that without revealing what you have.
Okay.
So then you reply with a bit. So how do you reply? You raise your hand or you don't raise your hands. Okay. And then you were trying. You win if this condition is satisfied. So you do some. What the hell is that? Okay. So if both of you have tails, then only one of you should raise your hands. Okay. You're not allowed to talk to each other. Right? So if both of you have tails, then only one of you raise your hands, and otherwise you should act in the opposite way. Okay? So so do something. Okay. What is that? There's no halfway.
Oh, you said only one of us.
No. You're either one of you can reply. I'm saying you win if, when we check all the data afterwards, if when both of you have tails, only one of you raise your hand.
Okay.
Yeah. There's no communication.
All
All right, so we're taking this as you raise your hand and you don't.
I'm raising my hand.
Okay, good. So
he doesn't
1.
know that, like, what she
What
has.
did your coin say?
Tails.
Heads.
All right, so you lose.
She said
Sorry.
one of his heads. Shoot.
So you lose. Okay.
Darn it.
So now, I'm not going to flip the coins again. You flip the coins. Uh-oh. No luck. All right, so let's play it again. You do something. All right. So you looked at her. No. You can do whatever you want. I'm saying the winning condition.
You are not allowed to look at
The
each
winning
other.
condition is if both of you have tails, then only one of you raises your hand. That's the winning condition.
Okay.
But you can act in whatever way you want.
You have to both react at the same time. Like,
Okay.
Yeah, you can't look
Then see
and
what-
you have to count
violate
down.
the locality
Okay.
loophole.
All right.
So, all right. So only one of you raised your hands, and then what? No. So what did you have?
Heads.
Heads.
Tails.
All right. So you lose again. Sorry. So you have a bad strategy. So
I think the
But I mean,
percentage
the
is
best
the one
thing
that
you can
anything
do is
goes
guess.
25%.
yeah. So
Because we can't.
But every once in a while, yes.
there. Okay. In the game, as in any game, you're allowed to strategize beforehand. You're allowed to use shared randomness, which is local realistic strategy, like
Okay.
the Einstein's language.
Okay.
Okay. So you're allowed to use shared randomness if you want. Turns out that doesn't help.
No.
You should just, oh, you know that, okay. So you should just behave in a deterministic way. What is the best thing you can do? Classic thing.
Well, I mean, we both have a 50% chance that we're gonna get one or the other. We just have to figure
That's
out
true.
which one that's gonna be.
No, but the point is that you should raise the hand when both have
When
a
both-
head, right?
Yeah.
Oh, so obviously you should never raise it.
No.
That's right.
Yeah.
You win
I like that
75%.
you intensely disagree,
Huh?
but
Oh,
you're right.
that's right.
No, I mean, of course you don't win all the time, but.
50-50 that we get one or the other, if neither one of us, if we
They
get
could
50-50
have a
and
separate
one
coin
of us
flip
raise our
and then
hand,
use the outcome of that coin
I
flip to
understood that,
coordinate their
you have to
strategy.
raise one.
They could do that.
But if
With
we
the
never
hand?
raise our hand, then we're only at a 50-50
They both get
loss.
heads.
So you have a better
Yeah.
chance. Why is that?
Then you have lost
Because we
There's a
both-
probability,
Lost and you win.
25%, that you get heads, heads, tails, heads, for each outcome,
Right.
right? So then there's a probability, 3/4 of the time, the outcome of the and, will be 0, right? So if you take heads, heads, and them, that's 0. If you take heads, tails, and, that's 0. Tails, heads, that's 0. And only 1/4 of the time do you get tails and tails. So then if you never raise your hand, that's both replying with a bit 0. And then when you take the sum, that's 0. So the equation can be satisfied 3/4 of the time if you simply don't raise your hand. So you do much better.
I think we should try it.
Well, if you do it, then it'll just work as a 3.
There are 4 possibilities, right? Appropriate answer is 1.
So, for a theorist, that's good.
Appropriate
But you
answer,
don't
no
know
one
it
raises
a
the
number of times.
That's also.
Yeah. Yeah, so, so we could repeat this experiment many, many times, collect statistics. If you never raised your hand, you would win 3/4 of the time. Yeah. Okay. So this is just a statement that shared randomness doesn't help. Are there any questions? There are many discussions. Are there any questions?
No, I want to hear what you two gentlemen are saying.
Yeah, why are y'all
Because
fighting?
you have a
Please
different
tell us.
perspective than I do. So what do you think?
I think
Oh, you don't understand the rules. Okay.
Aha,
I
okay.
think I do.
Okay, so if you follow the rules, then you can see, and then you do some math, then you can see that even with shared randomness strategies, so what do I mean by shared randomness? That's what Khalil was asking. Beforehand, y'all could have many coins, separate coins, flip them, and then make decisions based on the outcomes of those coin flips, in addition to the coins that you got from me, the referee, right? So that's a shared randomness strategy. That doesn't help in this game, okay? And that's to do with the objective function, the winning rule being somehow a linear function of the inputs, okay? So you work with that math, and then you see, oh, it's best to just do a deterministic strategy, okay? Yeah.
I have a question that it may be related or it may not be related. Can you describe, because this is something I still don't understand. So for example, we could not share that information. I mean, once you told us we could use classical strategies,
Yeah.
that would obviously help.
But by classical strategy, I mean the shared randomness, no communication.
Right.
Right, so
we-
after I flip the coins and give them to you, look the other way and don't say anything.
So right, so this leads me to my question of, which is something pseudo-related, is when people talk about, like, an all-quantum universal computer,
Uh-huh.
what would that look like? Because right now we have to have classical channels to communicate
Yeah.
the results to. So when you're talking about something all quantum,
Uh-huh.
where it's quantum, like, what does that look like, or what does that mean?
So, for example, with photons, if you interact them at a beam splitter, then that is a quantum interaction.
Okay, so
That can be
then how do
described
you
in a quantum
communicate
mechanical
that
way.
result?
So,
It's
so,
almost like a and not being able to.
So I could
how do
take
you know
the-
that you have something? Well, you know that you have something entangled, but how do we communicate that we know that the state was entangled? Like,
Okay.
We can't say anything.
so you would
Like,
do
you
your
would
measurements,
point-
you would do
yeah,
something
yes.
on your particles, and then report back to me, and then I would look at this winning condition. We haven't arrived at that point yet, we're about to get to it.
Okay.
Okay. But to make the entangled states, you could do something like take two photons, interact them at a beam splitter, and then one particle would get sent to you, the other would get sent to another. So we haven't talked about a quantum strategy yet for this game, right? We've only talked about classical strategies.
Right.
What is a quantum strategy? I could send you, or you could share beforehand a quantum state, a density operator rho AB. Somehow you could share that, right? It could be entangled. It could also be separable. If it's separable, it's not going to do better than classical for this game. Okay? But if they're entangled, you can do better. Suppose that you had a device that could make the EBIT state, the Bell state, the maximum entangled state, you know, the 0, 0 plus 1, 1. If you had a device that could make that, and then you could share that, then there's a quantum strategy that you could do where you could beat this classical limit. The classical limit we said was 75%, 3/4 of the time. With the quantum strategy, you can win 85% of the time.
But I thought the point was that no party knows anything about the system, not even the two parties themselves.
You would be allowed to know what row AB you share. You could know that.
So
That's like you get together beforehand and you devise some strategy. And then you say, okay, once the game starts, we're going to do this strategy.
okay,
So one of those strategies could be sharing the row AB.
but then we inherently know. the
That's
strategy.
fine. Yeah, that's fine. Classically, you could come up with a strategy, and then we said you could prove that with any classical strategy, any preparation beforehand, you would be limited to 3/4 success probability. Right? But the classical strategy would exclude once the game starts communicating. That's the main thing. So even with the quantum strategy, once it starts, you're not allowed to communicate. You're just allowed to share this entanglement.
Okay.
So that's how the game goes. That's how most quantum games go. Okay. You can prove the statement that we made. It's like a simple logic thing that you do with binary logic. We've gone over time, and so I won't say what it is. Basically, you write down all the set of equations that can be that you realize with a deterministic classical strategy, and you find that they cannot be simultaneously satisfied. That only 3 out of 4 of them can be satisfied. Okay, so you write that down, and then you see that. Right, and then that's what we said. You just report back 0. Just don't raise your hand. So. Okay, a quantum strategy is this. You can share the maximally entangled state beforehand, and then this is your strategy. If you receive the heads, you would measure sigma z. You would do a Pauli sigma z measurement. Okay, there's a way you can do that. Maybe with the polarization beam splitter, that kind of setup. Okay. If you receive tails, then you would measure sigma x. Okay? And then you would report that outcome as A, as what you report back to me. I'm the referee. Okay? And something to notice is that this sigma x and sigma z don't commute, and so there's somehow something quantum going on there with these measurements. And then if Bob receives heads, you would measure this operator. This is a Hermitian operator that you can measure. And then if you receive tails, you do this. You do this measurement. And then you report that outcome. And then what we can prove, if you use the laws of quantum mechanics, if you use this Born rule that we talked about, this strategy realizes a winning probability of 85%. Okay? I'm not going to show you that calculation. That's it's a somewhat long one, typically reserved as a homework exercise. So you can do that as a homework exercise. But what you see is that there's a significant gap between the classical and the quantum winning probabilities. Okay? So this is what's called violation of Bell inequality. If you take that language and reformulate it with this game that we came up with, this is what it amounts to. That a quantum strategy does significantly and detectably different and better than a classical strategy.
What is the x equals 0 and x equals 1? Isn't that the outcome of the measure? Because you first need to measure something, then measure.
Yeah, that's a very good question. So that's maybe not complete. So you decide what measurement you're going to do based on the coin value that you get, right? If it's heads or tails. So if it's heads, you do this. And then for this measurement operator, there are 2 outcomes. And then one we can assign as 0, the other we can assign as 1. And then that's what you report back, the measurement outcome. right? So if you get heads, you measure this.
You
And-
got both the coin and cubic then, and you both.
That's right, yeah, you have the coin, you have the qubit, based on the value of the coin, you measure the qubit.
Okay.
And then you report that back.
But what do you mean?
Thank you.
What do you mean by report? I thought either you raise your hand or not.
Oh, yeah, you report back in that way.
So if I see 1, I raise my hand. If the result
Yeah.
of the measurement of Z was 1, I
Yeah,
raise the hand. I see.
exactly, yeah. Yeah. So that's the game. And then this is actually a way, there's a very, Scott Aronson called this Bell's theorem on steroids. So if you were to do this game many independent times, and we would all observe that you were winning roughly 85% of the time, then we could infer that the only way you could have done that is by using this strategy, and that's it. Okay?
Is there always one unique strategy that would be
Yeah.
the best result?
So up to the errors, that, like suppose that you're winning 85% of the time minus epsilon, where epsilon is arbitrarily small. Then we could infer that the strategy that you're using is essentially this up to some epsilon
That's
error.
your tolerance.
Yeah.
Okay, some error tolerance.
So that's called Bell's theorem on steroids, and it's a way that you use to verify that you have entanglement in quantum cryptography or quantum computing, for distributed quantum computing. This entanglement we learned is a resource, and it's important to know how to verify entanglement, and this is one way you could do so. So it's also called classical leash for a quantum system, because we, the classical people, are using these classical bits to infer something about the quantum world that's underlying what you're doing. We proved, or we argued that if you're not winning more than 75% of the time, then you're just classical. But if you start exceeding that threshold and you're not violating these locality loopholes, then we can infer that in fact what you're doing must have been this, and you must have had entanglement. Okay? Yeah.
Is this the best known quantum? I mean, is it known whether this is the best quantum strategy?
Excellent question. That's another theorem you can prove. It is the best.
Oh.
There's
For what?
something called Cyrilson's theorem, after a guy named Boris Cyrilson. He was, I guess, mathematical physicist. Published this work in some obscure journal in the 80s, and it was completely lost for years, and rediscovered by quantum information people like 2 decades later.
Well,
So,
happens.
it's called Cyrilson's theorem. Yeah, it happens.